Undoubtedly, one of the most powerful ideas in statistics is the idea of a distribution. Most of you will already have seen distributions before, usually in the form of a histogram, or maybe a frequency table. And even at this stage, representing data in this way is already a huge improvement over just staring at a list of numbers. Because statistics isn't really about individual values, it's about patterns. So let's start with something familiar. Imagine we measure the heights of a group of, say, 25 people. In its raw form, all we have is a list of numbers, and honestly, this is one of the worst ways to visualize data. A common first step is to calculate the mean, and that's fine, the mean is useful, but it's only a tiny piece of the story. In fact, in some situations, the mean can be actively misleading. To add more context, we often calculate the standard deviation. This tells us how spread out the data is around the mean. Here's a concrete example. Imagine choosing between two machines that cut metal rods, each meant to be 1 meter long. You'd obviously hope that the average length from both machines is 1 meter. But if one machine has a very small standard deviation and the other a much larger one, the choice is obvious. The first machine produces rods that are consistently close to the desired length. That's information the mean alone simply cannot give you. Now, let's take another step. Instead of summarizing the data with numbers, we place it into a frequency table, or better yet, a histogram. And this is where things get interesting. Because now, we can start talking about the shape of the data. Is it symmetric? Is it skewed to one side? Are most values clustered together, with a few extreme values stretching things out? This idea of shape turns out to be crucial, because the shape tells us whether statistics like the mean and standard deviation are even useful. In extreme cases, you might see something like a U-shaped distribution, where most values lie at the extremes. Here, the mean sits right in the middle, a value that almost nobody actually achieved. In situations like this, the mean completely fails to represent what is typical. So hopefully now, you understand the significance of a histogram's shape and the way it changes how we view certain statistics, like mean and standard deviation. They only really help us understand data when the data is centralized around a particular value and symmetric. Fortunately, this is exactly what we will be focusing on in this video series, as this is what you will be tested on at A-level. But it also helps form the foundational concepts of working with distributions in general, for those of you thinking of taking statistics further. At this point, we need to make an important distinction. Even though we often talk about distributions while looking at histograms, a histogram is not a distribution. A histogram is just a visualization of data. A distribution, on the other hand, is a mathematical model, a way of describing how values tend to spread. Now, to connect these ideas, something remarkable happens when we collect more and more data. If we keep adding people to our height dataset and update the histogram each time, the shape starts to smooth out. Random bumps even out. Gaps begin to disappear, and gradually, a very familiar curve begins to emerge, the bell curve. And this isn't just a coincidence. When a measurement is influenced by lots of small, independent factors, the results often drift toward a normal shape. That idea is captured by the central limit theorem. This smooth curve is what we often call the bell curve, and this is our first real encounter with the normal distribution. At this stage, what we're really looking at is a frequency density curve. It's still grounded in real data, but instead of sharp bars, we now have a smooth shape that captures the overall trend. This is where distributions become truly powerful. Because now, instead of counting frequencies, we can start talking about probability. To do this, we reinterpret the curve one final time, not as frequency, but as a probability distribution. And here is the most important idea in this entire topic. All probabilities come from areas under the curve. For example, the probability that a randomly chosen person has a height between two values is simply the area under the curve between those values. Probability has become an area problem. And mathematically, that means it has become an integration problem. Now, don't worry, you are not expected to integrate the normal distribution by hand. In fact, the function itself is deliberately unpleasant to integrate. Instead, your calculator has a built-in function that effectively performs this integration for you. What matters is not the mechanics of integration, but understanding what the answer represents. And this is exactly what we'll be focusing on. In this video series, we're going to use the normal distribution to calculate probabilities from real data. We'll look at how the distribution is defined, how it depends on the mean and standard deviation, and how to interpret results correctly using diagrams, simulations, and calculator methods, exactly as required at A-level. By the end, normal distribution questions won't feel mysterious or formula-driven. They'll feel like what they really are: questions about shape, area, and sensible modeling of data.